Hello guys, today we're going to be covering section 3.4, which is just going to be the chain rule. So we've gone over the quotient rule, we've gone over the product rule, and some other variety of rules for differentiation. So the next one is going to be called the chain rule, and it's, to me in my opinion, it's probably one of the most powerful ones that you could use. Like the product rule and quotient rule, pretty cool, but low-key love the chain rule. That's honestly my favorite. And you'll see why, is because it's literally everywhere. And if you know how to do the chain rule pretty well, then I think you know how to do calculus pretty well. Alright, at least derivatives pretty well. So the first thing is, it's like, what kind of situation would the chain rule require? Like, let's try to build up a place where we'd actually use it. So let's just say we have, like the function f of x is equal to the square root of 1 plus x squared. So we can't apply anything yet. We can't use the quotient rule, can't use the power rule, can't use the product rule, because, there's nothing there of that sort. There's no product or quotient, no just general exponents that we could do. But, we could try to think about composition though. Maybe f can be written as, f composed with g, or, f is equal to f of g of x. And let's just say, that's true. We could see, here we have the square root, so f of x could equal the square root of x. Then g of x, which is our inside function inside the square root, could be 1 plus x squared. So f of x and g of x by themselves are differentiable. So f prime and g prime are nice, or I wouldn't say nice, but easy to find at the moment. And I'll say with known rules, known rules meaning the ones that we've learned so far. So this is kind of where we link to the chain rule. Maybe we could talk about, f prime in terms of, f of x and g of x and their derivatives. And that's where the chain rule comes in. So the chain rule. So let's consider g. G of x is is differentiable at x. And let's have f of x be differentiable at g of x. So again, so far my assumption might be weird, but just know that, what we say is that x is where we're at the point we're finding the derivative at. But whenever we do, whenever we want to do the composition, we want to find the derivative at the thing on the inside. In this case will be g of x. So that's just more of a technical assumption. That way, whenever we take derivatives, it's pretty nice. So if we have that g of x differentiable at x, f of x differentiable at g of x, then we have the composition function, or the composite function, which is equal to f composed with g, is differentiable at x. And we have a thing for f prime. F prime is given by, it's going to be f prime of x is equal to f prime of g of x times g prime of x. So what this means is that we take the derivative of f of x, and then we plug in g of x, and then we multiply by g prime of x. And I wouldn't want to say plug in so much as, we're plugging in g of x into f prime, but so much as that we're evaluating f prime of x at g of x. And that's kind of what happens whenever we do the composition. Is that, we're evaluating f of x at g of x. So we want to evaluate the derivative at g of x. So, if you remember Leibniz notation, the dy dx notation. So if we have, y is equal to f of u, and then u is equal to g of x, then we can find dy dx as it's going to be equal to dy du. So it's going to be, like the derivative of y with respect to the what it depends on, which will be u, and then times the derivative of, the inside u, which is going to be g of x. Well, derivative of u with respect to x, so du dx. So, this is kind of like, this is one of those intuitive things, which is not true at all. I mean, we can't really do. But the idea is whenever you want to find, these kind of derivatives, you want to make sure you're doing it right. You have to make sure there's like a dy here, a du here, dx here. So you might arguably say that these cancel. And that's kind of like what you can do as an intuitive check to make sure you have at least a solid idea of what's going on. If you could say these cancel, if you could look at them and, if they were normal fractions and they canceled and they gave you back what you wanted, then that's a pretty solid idea that, you might be doing it right. But again, it's just an idea, it's an intuitive idea for certain kind of examples. But let's go back to the original example that we had. F of x, or f of x is equal to square root of 1 plus x squared. And if you remember what I said earlier about what we said we could write f of x as a composition of functions as, f of x inside, f of g of x, which is complicated to say. But we can write it as a composition like this. I remember we said that, f of x could equal to like the square root of x. In this case, I'm going to switch variables a bit. I'm going to say f of u is equal to the square root of u, and then, g of x is equal to 1 plus x squared. That way, when we plug it in, we would just get back to here. So, again, for this formula, what we need is f prime of u, and we need g prime. So let's go find, f prime real quick. So remember, f prime of u is going to equal to, u to the 1/2. We've already done this before. Bring down the exponent 1/2 and subtract 1 to get negative 1/2. Then g prime of x, we just take a derivative here. We just get, 0 plus 2x, so we just get 2x. And then what we can do here is plug it into the formula. So remember that the formula for f prime of x is going to equal to f prime of g of x. So f prime evaluated g of x times the derivative of g of x. So again, f prime of g of x is equal to 1 plus x squared. So you get 1 plus x squared, and then the derivative of g prime of x is going to equal to 2x. And now we plug in 1 plus x squared into our function, f prime. So into right here, let's get 1/2. And now this is going to be u to the negative 1/2 is the same thing as 1 over the square root of u. So instead of writing it as, 1 plus x squared to the 1/2, and to the negative 1/2, I'm just going to write it on the bottom instead. So I'm just going to do 1/2 2 times the square root of 1 plus x squared times by 2x. And let me just, kind of color things in and kind of clarify what I'm talking about. So here's g of x, and this comes from, right here. And then remember, we just we plug g of x into the derivative, then we just multiply these together, and that's kind of it. We just have to know the formula, and once we kind of know the formula, it's not too difficult. But the idea is that, we have like an outside function f of x and we have an inside function g of x. And that's a really good way to think about the chain rule, is that, we have like two functions being composed with each other. So for the chain rule, we start with the derivative of the outside, plug in the inside, and then times the derivative of the outside. So to kind of clarify what I mean, what I'll do is kind of write down the words. So like for the chain rule, we work from like outside in. So, we differentiate f of x. So that way we get still f prime of x. And we evaluate it at, g of x. And then multiply by the derivative of g of x. All right, so really what's going on is we're differentiating the outer function. So remember, it's f composed with g, or really it's f of g of x, like this. So we're differentiating this to get f prime, and then we evaluate it at g of x, and we multiply by the inner function. Well, the derivative of g of x, but really g of x is the inner function. So the first thing we did was differentiate the outside to get f prime, evaluate at g of x to get this, and the last thing we do is multiply by the inner function, which was g of x, so then times g of x. Well, g prime of x, my bad. So, it's kind of like we'll take a bit to get used to at first. And it's not really that bad in terms of like, the just kind of plugging and chugging, but getting the intuitive idea of just like, what kind of composition am I doing, or what function should be which, can be kind of hard to get used to, and there's not really a right way to do it. But, as long as you like kind of keep things consistent and that the derivatives of g of x and f of x, then we don't really have an issue. So let's do a few examples, a bit more complicated examples. And we'll use the mindset of like, inner and outside functions. So the first one will be like I, which will be equal to y is equal to cosine of x squared plus 2x. And what we want is to find dy dx. Again, this just means the derivative, so it's going to be the derivative of cosine of x squared plus 2x. So this will be the the outer function, and this will be the inner. So what this will be equal to will be the derivative of the outer, so negative, the derivative of cosine is a negative sign, evaluated, so derivative of outside, it's going to be evaluated at g of x, where we evaluate at the inner. So x squared plus 2x. And then finally, times the derivative of the inner, so it's going to be derivative of x squared plus 2x, that's just going to be 2x plus 2. All right, so, as long as you can kind of break down, and if you can do these examples, the biggest struggle is, again, just kind of identifying what the outer and inner functions are. Sometimes it's clear, sometimes it's not. So as we go through more examples, I'll kind of show you we'll go through more different kind of rules that allow us to do more. So, we have cosine of x to the fourth. Oops. That was cosine of 4 to the x. That was an exponential function. So cosine of x to the fourth, or cosine of 4, cosine to the 4 of x. I don't know how to say that. So we're gonna start off with again dy dx. It's gonna be equal to the derivative of dx of cosine of x, and then all to the fourth because it's the same thing. So then the fact that we have this power right here to the fourth will be our outside. So just we'll say will be the outside. And usually you can just view it as x to the fourth. And then the inner function will be cosine of x. And then so again, last time, like what we did before, we did the derivative of the outside. So it'll be 4 times, x to the third. But then remember, we're not actually doing x just yet. We're evaluating at cosine of x, or evaluating at the inner function. So evaluating at the inner, so cosine of x, then times the derivative of the inner. So derivative of cosine of x is negative sine of x. So then what we get is 4 times cosine of 3 of the x times, well, put the negative out there, sine of x. And that's our answer. So you have to be a bit mindful of this stuff. And at the moment it kind of seems easy, but we can always make things more difficult. But one of the things we just did here is that here we had a function that we knew the derivative of raised to an exponent, or raised to some power. And what we got was just we could basically just do a power rule in some sense. So we do do actually have a rule for this whenever we have a differentiable function raised to an exponent. So in this case, the outer function was just of the form f of u is equal to u to the n. And our composite function was of the form y is equal to g of x to the n. Thus, what we got was, y is equal to f of u, which is equal to u to the n, where u is equal to g of x. So that's basically what we had going on. So we can, use the chain rule and the power rule to evaluate these derivatives. So if you remember the Leibniz notation, the dy dx notation we were talking about, this was equal to dy du times du dx. And remember what we said about dy du? That's just equal to, the derivative of y with respect to u. So this will just be, this is just a power rule is u to the n, so bring down that exponent and subtract 1. Then times du dx. And then that'll just be n times, well, it'll not be n, but now we're going to do that substitution of u is equal to g of x. So you get n times g of x raised to the n minus 1. And then finally, du dx will just be equal to, g prime of x. So what I like to do is just, you keep the argument the same. You basically treat the argument as if it's like a power, using the power rule, then multiply by the derivative of the argument. That's how I normally say it. When I say argument, I usually refer to like the inside of something. So like the argument of, this term right here would be g of x. So it'll be like, you just take 1 off the exponent, we'll bring down the exponent and subtract 1 while keeping the argument the same. Then you multiply the derivative of the argument. And alternatively, the way you could write that is, just d, d of dx of g of x to the n is just equals to n times, n the bracket g of x to the n minus 1 times g prime of x. That way you don't necessarily need to use that Leibniz notation. So now let's see, take a few derivatives. Let's use some more examples of this case. So I'm going to differentiate a few functions. The first one's going to be f of x is equal to 2x to the 5th plus 7x to the 4th raised to the 7. So, as we said, it's kind of like the power rule again, but now we have to keep in mind of like what the inside is, this is a composition. So our inside function g of x, this is going to be like, I'm just going to put this in g of x is going to be equal to 2x to the 5th plus 7x to the 4th, because that's basically like our inside function. So remember, the derivative is going to equal to, you bring down that exponent, so 7 times 2x to the 5th plus 7x to the 4th, then 7 minus 1 is 6, and then times the derivative of g of x, so 2x to the 5th plus 7x to the 4th prime. And then finally what we get is, 7 times 2x to the 5th plus 7x to the 4th to the 6th. And then the derivative of, 2x to the 5th plus 7x is just going to be 10x to the 4th plus 28x cubed. And that's going to be our answer. So again, it's not that bad. It's just, at least in these cases, it's obvious kind of what's going on. But there's more cases where you can have things be a bit more confusing, such as if you had the case of the derivative of cosine of x, if you had some repeated differentiation. But we haven't gotten there just yet. That's gonna be my last example, is gonna be something more complicated like that. So I was double checking my notes. All right. So the next example we're going to do is one with like tangent now. So we're going to let y equal to 1 over the 5th root of tangent x. And just in case, if you guys don't remember, this is the same thing as tangent x. So it's a negative 1 over 5. Because it's negative because it's on the bottom. The cube root indicates like, the 5th root or like 1 over 5. The cube root? Let's say 5th root. Yeah. Like the radical sign with 5 indicates 1 over 5. So that's why we're going to write it this notation, and then we can just use the power rule again. Well, like the power rule mixed with the chain rule. Actually, I'm going to skip up this. So we bring down that exponent, so negative 1/5. I'm going to subtract 1. And again, we're also going to leave the inside the same because we evaluated it at the inside. So negative 1/5 minus 1, that's just going to be negative 6/5. Then times the derivative of, the inside, so the derivative times the derivative of tangent x. And finally, what we get is when we simplify, is that they're going to get derivative of tangent x is secant squared of x. We're going to put the negative out there. And we get a 5 on the bottom due to this 5. And then we're going to move all this to the bottom as well. So we just get times tangent x to the 6/5. So, again, it's not too bad. But the trick is to know that, you need to keep this, keep the inside the same, take a derivative with respect to like whatever is happening on the outside. And then you would multiply by the derivative of whatever is on the inside. Then one last example. We're going to do g of x is equal to e to the secant of x. So remember, g prime of x is going to be equal to, so the derivative of whatever is happening on the inside, which is just going to be like e to the x. So e to the x is derivative of e to the x, just e to the x. And then we evaluate it at secant of x. And times the derivative of secant x. And that's just going to be e to the secant of x times secant x tangent x. And that's going to be the answer for that one. So lastly, the last thing we can do with this is actually find derivatives of exponential functions. We'll let exponential function with a positive base. If we say negative base, some things get wacky, and we preferably don't like to talk about it. Remember that when we had if it's a derivative of x, a to the x prime will be equal to f prime of 0 times I think it was a to the x. And one of the properties we got out of that is that e to the x evaluated at 0 is equal to 1, and that's kind of how we defined e, was to be the number that satisfies that. But remember that we had this, but we're going to build on that now. So well, not we're going to build on it, but we're actually going to write this out more formally, like what is f prime of a. So remember that we can write a as e to the ln of a, because e to the ln of a is also e and ln are inverse functions, so they basically undo each other. So then what this tells us is that a to the x is equal to e to the ln of a to the x, which is just equal to e times ln of a times x. Or write it as more normally as e to the ln of a times x, because the ln of a is just a number. So now we could do the chain rule. And the reason why we want to do the chain rule is because now we have e raised to some function again. So now we can, now we can use the chain rule to actually evaluate the derivative of this. All right, so we had d of dx of a to the x is going to be equal to d of dx of e to the ln of a times x. And then if you remember what we said before was that, we keep the inside the same. Well, we don't keep the inside the same, but we keep we do the derivative of, the outside, which is going to be e to the x. That's just going to be e to the x, and then we evaluate it at, x. We evaluate it at ln of a times x. We just get ln of a times x, and then we multiply by the derivative of, the inside, which is going to be ln of a. Because ln of a is just a number, so it's basically just like of the form 5 times x. So the derivative of 5x is just 5. So in this case, the derivative of ln of a times x is just ln of a. So then what we get is that, this right here was equal to a to the x. So we get a to the x times ln of a. Thus, kind of more clarifying about what this means is that d of dx of a to the x is equal to a to the x times ln of a. So let's just say we wanted to find, let's do an example of this real quick. We want to do, we want to find a few derivatives, so let's let f of x equal to 3 to the x. You want to find f prime and f double prime. So firstly, f prime of x is going to equal to d of dx of 3 to the x, which is going to equal to, according to the formula, 3 to the x times ln of 3. Then f prime of x, which is going to be the derivative of, f prime of x. In this case, f prime of x is equal to 3 to the x times ln of 3. But again, we can just pull out that ln of 3. But we want to do the derivative of 3 to the x. It's 3 to the x again times ln of 3 times ln of 3. And then what we just get in the end, whoops, I love that I typed a letter. Okay, what we get in the end is just 3 to the x times ln of 3 cubed. Well, and this whole quantity squared. And to kind of underline what we're talking about is, the derivative of 3 to the x is just going to be 3 to the x times ln of 3 according to the formula. So then, remember that ln of 3 is just a number, so let's just say we're going to blank it out for a second and just forget about it. And then we'll forget about it right here instead too. And then we take 3 to the x, take a derivative of that, and then that's how we get this. So just in case you were wondering where that extra, ln of 3 came from. It comes from the fact that, we took another derivative of 3 to the x, and that produces another ln of 3. All right, and then one last example. Well, actually 2 more examples, and then we should be done. Nope, I'm done. I'm dumb. It's just one example. So we want to differentiate the function y is equal to e to the cosine of x squared. So here we actually have 3 functions that are outside functions. here we have like e as our outside function. Here we have like cosine of x squared as our inside function. But you might be like saying like if you look at just cosine of x squared, here's an outside, here's an inside. So let's just ignore that for right now, and we'll get to that as we work on the problem. So remember what I said above is that from the chain rule, that we work from outside in, and that's basically what we're going to be doing. So we get dy of dx is going to equal to, the derivative of, the outside, e to the x, evaluated at the inside, so cosine of x squared, times the derivative dx of the inside, so cosine of x squared, and then that'll be equal to cosine of x squared times d of, not dx. So remember, the derivative of, the chain rule again is that it's going to be the derivative of the inside. Well, the derivative of the outside, my bad. All right. Sorry, that throws my brain off every time that happens, so you know how it happens. Okay, sorry. So, to repeat what's going on, actually, let me do a different color. So the first thing we did was took a derivative of the outside, plugged in the inside to get this, and then we have to multiply by the derivative of the inside, so d of dx of cosine of x squared. And now again, we have another chain rule situation right here. So then we multiply by the derivative of the inside, well, derivative of the outside, derivative of the outside function, the new outside function. It's confusing because that's our old inside function, but now we have to keep on going. This is what it means to be working outside in. So the derivative of cosine of x is equal to negative sine of x, but we need to evaluate it at the inside, so negative sine of x squared, then times the derivative of the inside, so times the derivative of x squared, and then lastly what we get is e to the cosine of x squared times negative sine of x squared, and then finally times the derivative of x squared is just 2x. So then our final answer is just going to be e to the cosine of x squared, put that negative on the outside, sine of x squared times 2x. Yeah, so this one's a bit messy, and I'll just do another quick example, but I'll go by it really fast to kind of let you guys know what my process is. So, basically what we did right here was just a very general setting. So we had, a function, let's say f of x is equal to, well, no, let's do capital F. Capital F of x is equal to f of g of x. Well, let's say, f of g of x, but g of x is equal to itself, h of x, no, let's not do that. Let's just put h of x inside. We basically had this kind of three-way composition. Three-way. I'm stupid, my bad. Should be better words than that. Basically, we just have, three functions being composed into each other. And then basically what we did to find f prime of x was we defined, the derivative of the outside, evaluated to the inside. And then what we did was we multiplied by the derivative of the inside, so g prime of h of x. But remember that, when we take another derivative of a composition, we take a derivative of the outside, evaluate it at the inside, and then lastly, again, we multiply the derivative of the inside, so times by h prime of x. And then one last example of what this would look like is if we did, cosine of e to the x squared. Basically a similar situation to what we did before. So derivative So, if you want to find f prime of x, we take the derivative of, the outside, we'll take the derivative of the outside function, so negative sine of x, evaluate it at the inside, times the derivative of the inside, so e to the x, so it's going to be the derivative of e is just going to be e to the x, just e to the x, evaluate it at the inside, times the derivative of the inside, which is just 2x. And here I'll kind of clarify, here our f of x is equal to cosine of x, our g of x is equal to e to the x, and our h of x is equal to just x squared. All right, so this is kind of what I mean by if you can do these kind of situations right here and you can understand which of these choices you have and how to build them, then it shouldn't be too bad whenever you actually solve these problems. But that's it for this section. Hope you guys liked the video. Like, comment, and subscribe, I guess. And let me know if you have any feedback on the videos as well. I always appreciate the feedback. If I can make things better for you guys, I'll gladly do that as well. All right, peace out.